Okay. Here's what it says, and I'll try and go through an example of it. The derivative of the antiderivative from a to x of f of t dt would equal just f of x itself. Right? So let me try to explain a little bit what that is saying. I'll do it through an example. Let's say we got the integral from 0 to x of cosine t dt. What is this asking you to find? Geometrically, what is it asking you to find? The area under this curve from 0 to x, where we don't know what x is. Okay? So, if you're thinking about it, you know, cosine starts up here at 1, right?
Yes.
And then at pi over 2, it's already down. It's back down to 0 already, and then it just keeps going and going and so on. Okay? So let's say x, obviously here's 0, let's say x fell right there. So then what we're asking you to find is we're asking you to find this area right in there. Okay? So, how do you think you would go about doing that? Let's do it using the first derivative. Alright? So, or excuse me, the fundamental theorem of calculus part 1. What is the antiderivative of cosine t?
Sine.
Sine.
Wait.
Just sine. Just sine. Because the derivative of sine is cosine.
Yeah.
Okay? So this would equal sine t. And then we'd evaluate that from x to 0, right? Using the fundamental theorem of calculus part 1. And so that would equal what? Now you plug x in, right? You get sine x minus what? Sine of 0. Well, what's the sine of 0? 0. So really you just have sine of whatever x is. Okay? So now, depending on whatever x value this is, that would be the answer to your area, if you will. Okay? So if x was, I don't know, pi over 6. Okay? If x was pi over 6, well, then the area under the curve from 0 to pi over 6 could simply be found by just doing the sine of pi over 6. We can prove that using the first fundamental theorem of calculus. Okay? Well, then what this is then showing you, is kind of like showing how they're inverses of each other. Okay? We just did this part right here. Okay? We used 0 to x, and then we had cosine t dt. So, what the fundamental theorem of calculus part 2 is saying, well now if you did the derivative of that, you would just get the original function itself. So in other words, now to kind of finish off this second part here, we did this right here. Well, what if I asked you, what's the derivative with respect to x of sine x? Cosine x. So do you see how we're back to the function we started with, but now it's with the variable x in it? So it's kind of showing you, in a sense, how derivatives and antiderivatives are inverses. They undo one another in a sense. And if you ever need to find the antiderivative of a function with respect to a variable that's different than the variable that's here, doing that and then doing the derivative of it will just get you back to that function itself, that function that we started with in there. Okay? So, let me do another example, or one similar to maybe one that you're going to have. We are on page 295. Let's look at number 81. So it says, find f prime of x if f of x equals the antiderivative from -2 to x of t squared minus 2t dt. So we want to find the derivative of f of x. That's what this is saying. If f of x is equal to the antiderivative of -2 to x of t squared minus 2t dt.
So it's like find the derivative of the antiderivative?
Yes. These problems are that simple. And sometimes to me, it doesn't quite make sense because it's so obvious.
Yeah.
To a degree. Okay. So f of x is this part right here. Okay? Because f of x is sort of -2 to x. Here's my f of t dt. Okay? This is going to be as easy as you think. Basically, your answer, because they want you to find the derivative of this, which the fundamental theorem of calculus is saying the derivative of this is just the function with respect to x. So my answer is simply going to be f prime of x is equal x squared minus 2x. That's it. And
That wasn't right.
I'll show you why.
Why are we working with p's here?
Okay?
'Cause you have
Just to
that-
show you if there's a change in the variable and you're trying to find the area from -2 to potentially different values. So instead of always being a set, I'm going to find the area from -2 to 2. Then I'm going to find the area from -2 to 3 or -2 to, wherever. Basically I'm saying no matter what this x value is, you have multiple x values or different values that I'm finding the area of, and it'll always come back to the function itself, I guess, instead of it always being a set lower bound and upper bound. If there's a variable in the lower upper bound, basically. YTs, I don't know. Use Y's or whatever you want to use. Okay? Let me show you why that works using the first part of the fundamental theorem. So -2 to x, t squared minus 2t dt. So let's just use the first one. Let's do the antiderivative of this. I would get 1/3 t cubed minus t squared, right?
Yes.
And that's from negative 2 to x. So then let's plug that in. I get 1/3 x cubed minus x squared.
Are we gonna have to show this work?
Nope.
Okay.
I'm just showing you why it works and why it is as simple as it seems. Okay? So I plug in the x and get that, right? Then I plug in the negative 2. Negative 2 cubed is negative 8, so times that'd be negative 8/3. Negative 2 to the second would be 4. So I get 1/3 x cubed minus x squared. Negative 8/3 minus 12/3 would be negative 20/3, but I'm subtracting a negative 20/3, so it'd be plus 20/3. Okay? So there's f of x.
Where did we get the negative 8/3 minus 4?
I plugged in negative 2
Alright.
here.
Yep.
Just did a bunch of math with fractions. So when they say that f of x is equal to this, they're really saying that f of x is equal to this. But what were you asked to find? F prime of x. Okay, so do the derivative of this real quick. What's 3 times a third? 1 x to the second. What's the derivative of negative x squared?
2x.
Negative 2x. And what's the derivative of 20/3?
Nada.
0. So that's why this is your answer. Okay? So it almost seems so simple. Okay? Basically, the biggest thing I want you to kind of understand is how the integral represents an accumulating area. Like if I did that cosine one again. If I found this area, and then I found this one added together, and this one added together, and that's really kind of what we're doing. The area, the derivative of the antiderivative is like finding the accumulated area over time. Okay? So, that's really all the second derivative is. It's fairly simple. Your practice is page 295. 82 to 85, and then number 74, which maybe we should do 73 together in class to help you do 74. Might not hurt. How long is my video on? I don't want it to be too long. To 12.
Like 74.
Oh, 82 to 85 and 74.
So we're gonna do 73?
I'll do 73 with you. That'll help you with 74.
Perfect.
I'm on page 295. Alright, so f is shown in the graph on page 295. You'll want to be able to see that. Okay. Alright, so it says find g of 0. Well, g of 0 would represent the area under the curve f from 0 to 0. Well, what's the area under the curve from 0 to 0 going to equal? 0, because it has no base value, right? There's no width to that area that you're finding. So g of 0 is 0. G of 2 would be asking you to find the area under this function f from 0 to 2. Okay, well, if I go to that picture, if I want to find the area under the curve from 0 to 2 and I had to kind of estimate it, 1, 2, 3, 4, 5, 6, 7 maybe? Close to 7?
Close enough.
because we're estimating, right?
It's a little over, but it's close.
Okay, close to 7. How about G of 4? G of 6? G of, do we do 8?
No.
Yep. Estimate those. I'd say about 9 for G of 4.
Yeah, it's a little high, but.
Okay. Alright, and 6. Probably take 1 off and go back to 8. Because it'd be negative.
Yep.
Take another 3 off.
Oh, maybe it's this one thing.
Take another 3 off maybe.
Yep.
For 5.
What? Oh, is it the area?
The area.
Oh, you estimating?
Yeah.
Yes.
Oh, okay.
Oh, okay.
Yeah.
Did you see?
I thought it was like
so confused.
G of 4 equals 9.
No. Because G of 4 would represent the area from 0 to 4 under that function.
Oh.
So I'm looking from an x value from 0 to 4, and I'm estimating the area under that curve down to the x-axis. Just estimating by basically counting boxes.
I got you.
We did that on the test yesterday.
And anything below the x-axis is a negative area, so that's going to take away. Are we okay? Back good? You guys?
For
Right?
G6.
Right? Huh?
G6, how did you do?
Well, to me, if this was 9,
Yeah.
if I, looking at the area from 4 to 6, you kind of got about 2 of those.
Oh my.
One of the boxes maybe is about a third of a box, the other one's about 2/3, so I thought together they would maybe make about 1. So that's why I just took 1 off there. I'm estimating, Zach. It's rough.
Alright.
But you can't see what I did there?
Yeah.
Okay. All right. So, it says find the largest open interval. Part B says find the largest open interval on which G is increasing. So where was the G function's value increasing? From where to where?
From 0 to 4?
From 0 to 4. Because at 0, G, the function G, had a value of 0. And then at 2, it had a function of 7, so it's definitely been increasing. Then it got all the way up to 9. But as soon as we got past G of 4, the value started going down because you started adding those negative areas. So for part B, I would say it is increasing from 0 to 4. Find the largest open interval on which G is decreasing then. So you'd say it's decreasing from where to where?
4 to 8.
From 4 to 8.
Mm-hmm.
Okay. Identify any extrema. So that'd be like a maximum or a min.
Local max or like?
Mm-hmm. Yep. So which one of those could have been a max? Or it looks like it'd be a max.
0 to 1.
I mean, if I think of this and I drew a sketch. G of 0 was 0. G of 2 was 7. G of 4 was 9. G of 6 was 8. G of 8 was 5.
That's what I said like this.
Okay? So I guess to me the graph looks something like this.
Okay, so then 4.
So do you see an extrema?
4.
Where? So G of 4 equals 9. Or if you think of it as 4 comma 9, however you see it. Where the value of this function, the value of the G function, is representing the area under.
Wouldn't G of 0 be the min then?
It's kind of hard because that's an end point to know. You don't want to use your, if it said define the extrema on the interval 0 to 8, so it gave us a closed interval to check for extrema, then yes. But because it just said find local extrema just in general, it didn't give us an interval to check. You don't want to check the endpoints because you don't know, I mean, does it keep going down, you know, on the endpoints? You want to just check anywhere on the open interval, okay? So, 74 is similar, but it kind of gives you an idea of the accumulating area, all right? The accumulating area under the